Hi guys, Ryan from Mechanic.com.au, Australia's #1 mechanic community, and today we take a look at variable geometry or variable nozzle turbochargers. Variable geometry turbos have been one of the most effective ways of increasing engine economy and performance over the past years. But like with most things, the more complexity and moving parts we add, the more susceptible something generally is to failure. Let's take a look at the basic operation of a typical variable geometry turbo and some of the most common reasons for failure. If you've ever taken a compressed air nozzle and aimed it at a fan, you'll know that as you move the position of the airstream in respect to the fan, the speed increases and decreases. This is the same basic principle that variable geometry turbos use to effectively change the aspect ratio of the exhaust housing. We change the angle that the exhaust gas hits the turbine to alter the turbocharger shaft speed. This is called the angle of incidence. With a conventional turbocharger, this angle of incidence is fixed. We cannot change that angle or velocity of the air that hits the fan. A variable geometry turbo uses an actuator to control what's called an exciter ring. The exciter ring is a moving part of the turbocharger that changes the pitch of the internal vanes and can be controlled electronically, hydraulically, or pneumatically. The greater the pitch of these vanes, the higher the exhaust back pressure and the faster the turbine spools up, resulting in less turbo lag and better torque. At higher RPM, the vanes typically relax, which reduces exhaust back pressure and regulates turbo speed and boost pressure. While electronically controlled turbos are arguably the fastest and most precise method, it also has one of the higher failure rates, especially on earlier petrol applications due to high exhaust temperatures. This has been alleviated through the use of water cooling and engineering changes to actuator construction. Here we have a whole set VGT off of a 14-litre Detroit diesel engine, and this system works a little differently. Instead of changing the pitch of the vanes, they're fixed. The actuator moves the entire vane plane axially in relation to the turbine wheel. This results in less moving parts and generally a longer service life. This style of VGT is found mainly on heavy vehicle applications. For three of the other most common points of failure on variable geometry turbos, as well as tips to extend variable geometry turbo life, check out our article linked below. This video is brought to you by our friends at Penrite, proudly Australian owned and operated for 90 years.